All right, so where did it all come from, right? Where did all the atoms come from? Nobody knows, of course. The leading theory is that some sort of big bang event, right, where all of the material in the universe was concentrated in a single point, and people are, cosmologists and theoretical physicists argue about this. That's beyond the scopes of chemistry. Chemistry actually doesn't make a lot of sense when you're talking about the very early stages of the universe, because electrons and all the other subatomic particles don't really have individual identities. They're all aggregated together and sharing quantum states and stuff. So there actually isn't chemistry in the early universe. But once you get to chemistry, right? Once you get to actually having hydrogen atoms, then we can talk, right? Then we can talk about inorganic chemistry and chemistry of the universe. And so that's where you get into stars, and stars being element factories. And so how does this work? This works through fusion, right? This works through E equals mc squared, Einstein's famous relationship that tells you that mass and energy can be interconverted, right? So you can release, you can convert mass to release energy, or vice versa. And this plot here, so you have hydrogen, okay? Once you have hydrogen, the primary reaction, nuclear physics reaction that's happening inside of stars is hydrogen getting converted into helium. So often we'll use the term hydrogen burning to helium, but it's not burning in our earthly sense. Burning in our chemistry earthly sense means hydrogen plus oxygen goes to water, right? I'm not talking about, there's no oxygen in these stars, okay, or not significant amounts. We're talking about fusion reactions. So it's actually, two hydrogen atoms coming together and making a helium atom. In the process, giving off light and heat, and that is the primary mechanism by which stars exist, okay? Hydrogen is the primary fuel of all stars in our universe. What's very interesting is, you can do these nuclear physics calculations and show that basically this is the binding energy per nuclear particle. And so this is getting higher and higher. You're getting tighter and tighter binding, okay, until you get to iron. It actually peaks at iron. And iron is special in these sort of nucleosynthetic pathways because it's the highest element that can be made in a normal star, okay, just through these fusion processes. And so to get elements that are higher than iron, basically. So the star can go hydrogen plus hydrogen goes to helium, helium plus hydrogen goes to lithium, or helium plus helium, right? It can keep building up this way, up to iron. And then there's other processes that occur primarily through more exotic, interstellar events such as supernova explosions that we don't have to really go into details. But you can get these higher elements, okay, beyond iron. Obviously, our Earth contains a lot of iodine, gold, lutetium, all these other elements that are clearly much heavier than iron. So they have been produced and we ended up with them. Okay, but up to iron is where you're going to be energetically favorable to do fusion reactions. You can do that all the way. Then you have these other events that make you all the way up to uranium. Past uranium, the atoms are getting too big, and so they're going to undergo fission. Okay, and so they will spontaneously decompose. And this is where you have nuclear reactors. This is what we've taken advantage of on Earth. You think about like uranium fuels, or thorium fuels, or plutonium waste, or missiles, nuclear missiles, things like this. These are all operating via fission reactions. So all of our nuclear power plants are through these heavier elements doing fission. They're taking mass and going into energy in that way. Okay, so stars in this way are element factors. This is where all the elements came from, and that's why we are very literally star stuff.